What's up, guys? I'm Chad Barnes, and welcome to the channel. Here, it's all about real car talk, from simple fixes to smart driving tips and keeping your ride in top shape. If that sounds good to you, go ahead and give the video a thumbs up. Hit that subscribe button and make sure you watch all the way through. There's a lot of good stuff coming. Let's get to it.
How do light commercial vehicles differ from passenger cars? First of all, they are optimized for cargo transportation. Passenger cars are sometimes loaded like donkeys, but not all owners do this, and it doesn't happen very often. This means that LCV tires are regularly subjected to much heavier loads, and this requires appropriate design modifications to withstand these loads. And secondly, as a rule, the daily mileage of commercial vehicles is many times higher than that of passenger cars, unless, of course, the passenger car in question works as a cab. As a result, the issue of resistance to wear and tear and durability comes to the forefront because the system of priorities of private car owners and LCV operators has very significant differences. For the owner of a passenger sedan, hatchback or crossover, acceleration and braking dynamics, handling, comfort and noise will be at the top of the list, and customers are willing to pay, and sometimes quite a lot of money, to improve these parameters. Owners of commercial vehicles also pay attention to these parameters, but the main for them are issues related to economics, the initial price and durability, i.e. service life. It is clear that many of these parameters are in contradiction, and these contradictions become especially vivid in the case of the development of winter tires. Judge for yourself. To ensure maximum grip at low temperatures, the tread compound must be as soft as possible. But in order to provide the best abrasion resistance and therefore long service life, the compound must be hard. In order to reduce fuel consumption, and this parameter is also critical for LCV owners, it is necessary to reduce rolling resistance. But a stiff rubber compound is also better suited for this. And such a picture turns out: we improved fuel efficiency, and at the same time increased durability, but at the same time grip and controllability deteriorated. They used a softer compound, increased comfort, reduced noise, increased controllability on wet asphalt, and in snow mush, performance indicators deteriorated. Nose out, tail bobbed, tail out, nose stuck. As a result, the development of a perfectly balanced product becomes an incredibly complex task, requiring the involvement of all available intellectual and technological resources. How tire manufacturers solve the task set before them. We will look at the example of Toyo Tires. Back in 2011, it introduced the Toyo H09 commercial winter tire. This model embodied almost all the technologies available at the time: tread compound with improved wear resistance and a carcass profile for even distribution of contact pressure guaranteed a sufficiently long service life, tread pattern with wave sipes provided, high lateral and longitudinal traction on wet and snowy roads, and strong steel braces together with reinforced bead construction. Minimized internal stresses in the carcass during the treading process. Talking about the summer tire Toyo Nano Energy van, we have already noted that the life cycle of individual tire models for light commercial vehicles is much longer than in the case of passenger car tires. In passenger car lines, manufacturers try to introduce a successor every 5 years, but the average life of a commercial tire model is 10 years. So the replacement for the H09 model appeared in quite expected time. When working on the new model, called Observe Van, the designers set themselves the following objectives: to improve the performance of the tire on wet surfaces, in particular, to reduce braking distance, as well as to improve handling and stability, to improve handling in snow, to increase the life of the tire by strengthening the carcass and increasing the wear resistance of the tread. At the same time, the rolling resistance had to meet the Category C-E wet grip, Category B, according to the European tire marking system, and the noise level should not exceed 72 dB. And with these tasks the designers have successfully coped. Now let's see how they managed to achieve the specified indicators. Let's start with the first thing any user sees: the tread pattern. At first glance, the pattern is very similar to the tread pattern of the new Toyo Nano Energy Van summer tires, which began sales in the spring of 2020. The same 4 rows of blocks, 2 rows of center blocks connected into a double center rib with a zigzag groove, and 2 rows of wide shoulder blocks. This pattern increases overall stiffness, which means better handling and wear resistance. The main difference between the Winter Observe van and the Summer Nano Energy van is the presence of many wave-shaped 3D lamellae, cutting both the center and shoulder blocks. A closer look reveals other differences. The edges of the transverse grooves separating the tread blocks are staggered to improve traction on snowy surfaces. The performance of a tire depends not only on the tread pattern, but also on its internal construction. In this case, the Winter Observe van and Summer Nano Energy van are structurally very similar, in both cases, directly under the tread. There is a spiral weave breaker layer that provides uniformity of performance over the entire circumference of the tire. Underneath the tread there are layers of high tensile strength metal cord, and underneath the metal cord there is a multilayer cage made of high stiffness polyester. But the main design feature of the Observe van tires is a powerful bead reinforcement built into the sidewall of the tire. When compared to Toyo H09 tires, it was found that this structural element is able to reduce internal stresses and amplitude of strain energy density by 75%, which in turn has the most significant effect on increasing tire life. It is worth noting that both the tread pattern and the internal design of the Toyo Observe van were developed using the T-Mode computer aided design and modeling system. We have already described what this system is and what advantages it brings, and in some detail we just want to emphasize that one of its blocks is a mathematical model describing the interaction of the tire with snow and allowing real-time prediction of tire behavior on snow, as well as estimation of friction forces between snow and rubber under conditions of loads and speeds corresponding to the conditions of use of a real car. Snow is a very complex environment in terms of modeling its interaction with the tire. A lot of parameters have to be taken into account, including snow particle size, density and water content. But all these difficulties have been successfully overcome, and now T-Mode technology makes it possible to visually assess tire characteristics that are difficult to measure in an experiment, for example, how the tire deforms and how the pressure in the contact patch is distributed at speeds above 100 km per hour. It is very difficult to obtain such data by direct measurement, even with the most advanced sensors. It is the use of T-Mode technology that has enabled the Observe van to achieve a 27% increase in stiffness and ability to resist deformation loads during braking in the shoulder blocks, and a 51% increase in the center rib area compared to the Toyo H09. And, of course, achieving these goals required serious work to create a rubber compound with the required parameters, and, as already mentioned, it was necessary to achieve a balance between directly opposite requirements, maximum resistance to abrasion and elasticity at low temperatures. And it is unlikely that Toyo specialists would have been able to obtain the required parameters if it had not been for the nanobalance technology that had been developed by that time. The essence of nanobalance technology is to work with the rubber compound at the molecular, i.e. nanolevel. This work consists of several stages. In the first, the fillers and polymers of the rubber compound are thoroughly studied at the molecular level. During this study, the responses of the observed molecular structures of the rubber compound under different driving conditions are analyzed and tested. In the second step, molecular dynamics simulations are performed based on the collected data in order to suppress the physical movement of rubber molecules. Such suppression reduces heat generation, hence energy loss and reduced rolling resistance. However, the rubber compound is called a compound because it contains many other substances and compounds in addition to rubber elastomers. In the next step, the behavior of the various components that make up the compound is modeled using the finite element method. Engineers achieve minimization of friction between the components and reduction of stress concentration zones, and the quantitative and qualitative composition of the mixture is selected on the basis of the constructed models. The final stage of the nanobalance system is the control of filler compounds and their optimal dispersion during the production of the rubber compound, and this control is also performed at the molecular level. The result is quite impressive. Of course, all companies keep the composition of their rubber compounds a secret. We can only note that the compound of Observe van tires is characterized by an increased content of silicon dioxide, which seriously increases the mechanical strength of the rubber. However, the possibility of increasing the mass fraction of silicon dioxide in the composition of the rubber compound is seriously limited by one circumstance. Chemists are well aware of the principle like dissolves in like. So, rubbers and other polymers are completely different in their chemical properties from silicon dioxide, and their combination can be compared to an attempt to mix oil and water. What we end up with is not a homogeneous mixture, but individual large clumped conglomerates of filler and individual areas of the rubber mass that have no filler in them. During compression tensioning, the filler clumps will crack and collapse, which will use up extra energy and therefore increase rolling friction. Toyo observed Van Tire to overcome these contradictions. Toyo's chemists had to introduce polymer molecules into the mix, which they call a new super-active polymer and a polymer responsible for snow performance. The specific chemical formulas of these polymers are kept in the strictest secrecy, and we can only assume that the former are responsible for masking silica molecules, which allows them to be evenly distributed in the compound and connect to the rubber molecules, but the latter are responsible for improving grip on the road surface. In fact, both traction and rolling friction are controlled by the same parameter, the loss coefficient. Only rolling friction is controlled by the loss coefficient at low strain frequencies in the tire, while traction is controlled by the same coefficient at high strain frequencies. As a result, the nano-balance technology has made it possible to find the compound that optimizes the values of these coefficients. Well, the final efficiency of the new tire is determined by the combination of the properties of the tread pattern, internal structure, and composition of the rubber compound. We can state that the comparative polygon tests of Toyo H09 and Observe Van showed that the new tires had an 8% reduction in wet braking distance, a 23% reduction in rolling resistance, and an 84% increase in carcass durability. In general, if you look at the diagram of changes in various indicators, you can clearly see that only one parameter has remained unchanged: braking dynamics on snow, and all the others have undergone a noticeable improvement, and the greatest growth we see is in the life of the tire. This means that the owners of commercial vehicles have received exactly the winter tires they need, with high efficiency on snowy and wet asphalt, with low rolling resistance, allowing to save fuel, but most importantly, with a long service life. In conclusion, the journey of tire longevity is a testament to the innovative engineering and advanced materials that manufacturers employ to ensure safety and performance. By understanding the intricate balance of tread design, rubber compounds, and manufacturing techniques, we can appreciate how tires are crafted to endure distances of up to 50,000 kilometers without the need for replacement. As we continue to drive towards a more sustainable future, these advancements not only enhance our driving experience but also contribute to reducing waste and promoting environmental responsibility. Thank you for joining us in exploring this fascinating topic.